Alright, what I'm going to do here for you is show you how to do the quiz that we took in class today. The kinetics quiz was a very basic kinetics quiz. You need to read the blog to see what I have to say about this and to see what you need to do about whatever else it is that you need to do. I'll have them graded for you on Friday. You can make your decisions then. But essentially, I'm going to show you and then you need to take a look at what I have to say. Alright, so the first reaction that we have here, or the first problem that we have, is to try and figure out what the order for these two reactants is. I've got NO reacting with H2 according to the balanced chemical equation above. But that's not necessarily how the rate's going to go. To look at how the rate's going to go, I have to look at the data and see how changing the concentrations of those particular reactants changed how they affected the rate of the reaction. And so in part A, we'll start by looking at H2. If I look at H2, I need to find places where NO is not changing. That looks like reactions 1 and 2. So for H2, we'll look at reactions 1 and 2. So essentially, if I take a ratio of those concentrations, so if I take the concentration of the second reaction, divide it by the concentration of the first reaction, raise it to some power, it should equal what happens to the rates. The rate change from 2 to 1. We just have to be judicious about how we make our selection so that we possibly don't have to deal with fractions. Not that that would be a huge problem, but it makes things easier if we don't. I've selected in reactions 2 and 1 so that hydrogen goes from 0.002 down to 0.001 concentration wise, and that will be related by an exponent to what happens to the rates, and the rates go from 3.6 times 10 to the minus 4 down to 1.8 times 10 to the minus 4. So essentially we have this part being 2 to the x power must equal 2. And so the order with respect to hydrogen is 1. So we're going to say first order in hydrogen. Okay? Now, we have to repeat this same process for NO. So for NO, the two reactions that are the same for H2 are reactions 3 and reactions 4. So we're going to use 3 and 4. And so doing that, we'll set up the same scenario. Because hydrogen's constant, I don't care. In reaction 4, which is what we'll put on top, NO goes from 0.002 down to 0.001 in reaction 3. That to a different power is going to be equal to the change in the rates. In this case, the rates change from 1.2 times 10 to the minus 4 to 0.3 times 10 to the minus 4. And so we see that a two-fold change in the concentration to some power gives me a four-fold change in the rate. And so the exponent with respect to NO is 2. So this is second order in NO. So over here, determine the order for each of the reactants. First order H2, second order NO. We're at the rate law for this reaction. Well, now I know what the coefficients or the exponents of my rate law are, so I'm just going to write them. The rate is equal to the rate constant times hydrogen gas to its power, which is first, so it's understood, and NO second order means second power. So that's easy enough. Then it wants me to calculate the value of the rate constant. Well, at this point, I just select one set of the data and use it. How about we just use reaction number 1? That's easy enough. So for reaction 1, dot, 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 the rate that I have for reaction 1 is 1.8 times 10 to the negative 4. That's got to be equal to K times hydrogen's concentration, which is 0.001, times the concentration of NO, 0.006, and that has to be squared. And so I see then that my rate constant, K, is going to be equal to 1.8 times 10 to the minus 4 divided by 0.001 times 0.006 squared. And K, if we do that math, is about 5 times 10 to the minus, or 10 to the positive, sorry, 10 to the third. And the units on that, since the overall order is to the third, it's going to be m to the negative 2. And our time in this case is minutes, and so it'll be time to the negative 1, so minutes to the negative 1. And so that is K. Alright, next part of this wants me to look at experiment 2 and calculate the concentration of NO remaining when exactly 1/2 of the original amount has been consumed. Well, originally, if we go back, we see in reaction 2 that we started with 0.002. So I'm starting there, and I'm starting with 0.006 for NO. So I'm going to carry both of those values over to the front. So right here we'll say the concentration of H2 initial equals 0.0020, and the concentration of NO initial equals 0.0060. So it wants to know how much NO is remaining when exactly 1/2 of the original H2 has been consumed. So it's safe then to say that the concentration of H2 at some point in time is going to be 1/2 of H2 initially, which would be 1/2 of 0.0020 molar, and so should be 0.0010 molar. Now, something we haven't noticed yet or taken a look at is what size container we're in. It doesn't really say what size container we're in. It just says I have that much in a mole per liter. So what we're going to do is make the assumption that we have a 1 liter vessel. That's going to make me be able to treat all my molarities as concentrations. And so we'll go right here. If I'm down to 0.001 molar, let's look what must have happened then to my NO. If I have 0.0010 moles of H2 in every 1 liter, and I have 1 liter vessel, and I also know that there are 1 mole of NO consumed every time 1 mole of H2 reacts, then I can see that I'm going to lose 0.0010 moles of NO used as well. So then the concentration of NO at the same time as the H2 is going to be equal to NO initial minus NO used. And this is all because we're in 1 liter. So that works nice for me. So the concentration of NO at that time is going to be equal to 0.006 moles, which came from the liter, minus 0.001 moles, all still in the same 1 liter container. So we've got 0.0050 molar. So basic stoic. Basic stoic. That's all that is. Alright, moving on. Last question. Says the following sequence of elementary steps is proposed for the mechanism for the reaction. Based on the data presented, which of the above is the rate determining step? Show that the mechanism is consistent with it. Alright, so here was my rate law. I'm going to go ahead and write it down because the slow step has to match it. Rate equals K times H2 times NO squared. So essentially what I have to have is I have to have a rate law that incorporates two NOs and an H2. So I can't use this as the slow step. That wouldn't give me any H2. So this is not it. I can't use this as the slow step because that would incorporate NO, two H2s. Can't have that. So the only one it could be is right here. So this must be the slow step. So show that the mechanism is consistent with that. Okay. So in my rate law, I'm allowed to have everything up to the slow step. So everything up to here. So if I look, this is an intermediate. So I'm going to mark out my intermediates. What reactants then are reacting? I've got NO, NO, and H2. So according to those two elementary steps, my rate should equal K H2 once to the first power, NO occurring twice, so that's NO squared. Is that consistent with this? Yes. So I'm happy. Alright, now we need to show it's consistent with the overall stoic of the reaction. Essentially that means that these three steps must add up to produce this. Do they? Let's take a look and see. My reaction says NO plus NO makes N2O2. My next reaction and the one after that go beneath them. So in this one I've got N2O2 reacting with H2 to make H2O and N2O. And then down here I've got N2O reacting with H2 again to make N2 plus H2O. Now we just need to add this up and cancel out all things that appear on both sides of the reaction and see if it matches the original stoic. We said this was an intermediate a minute ago, so we're going to cancel it out. N2O, also an intermediate. Anything else? No. So according to this, we get 2NO plus 2H2 makes 2H2O plus N2. Is this consistent with this? Yes. So once again, we're happy. This mechanism is a valid proposition for how this reaction occurs. It matches the rate law, as we see here, and it matches the overall stoic of the reaction, as we see there. Again, please go look at the blog and see what else is going on with this and what you need to know.